Today we're going to talk about quadratic splines, and to be a little more specific, we are going to have endpoints x sub I comma f sub I, and because we have endpoints, we'll be able to connect those with n minus 1 quadratic splines, and I want you to be able to kind of envision that. So I'm going to put in a little sketch here. Actually, let's make this our x-axis. I'm just going to move it down, and let's put in a y-axis as well. And I'm going to sketch in some just random points here. So let's say that this is what our data looked like. We had 4 points instead of n. According to this, there should be 3 splines. Let's just see that that's the case here. Let's go ahead and connect the first 2 points. Let's go ahead and connect the next 2. And then on to the last one here. Pick a different color. Right, and so that gives us 3 of these. All right, so we see that that's true. What do these quadratic splines look like? What's their equation? Let's see what that would be. So we're going to have s sub I of x is equal to a sub I plus b sub I times x minus x sub I plus c sub I times x minus x sub I squared. The next thing we're going to do is we want these quadratic splines to go through these points. So what we're going to do is we're going to plug those points into the quadratic splines. So that's going to look like f sub I is equal to a sub I plus b sub I times x sub I, because that's what we're plugging in, minus x sub I plus c sub I times x sub I minus x sub I, and then squared. And so if you simplify that, right, we get some terms that are 0, so this just becomes f sub I is equal to a sub I. So by writing our quadratic splines in this fashion, we've reduced our number of unknowns. So at this point here, we had 3, right, because we have a's, b's, and c's, and we have n minus 1 quadratic splines, so we had this many unknowns. But now we know all the a sub i's, so we've reduced the number of unknowns to 2 times n minus 1 unknowns. Let's keep going here. So the next requirement that we have here is that we want the function value of adjacent polynomials to be the same, okay? At least at the knots. So let's go ahead and set this up. This is what it should look like mathematically here. So the ith spline should look like a sub I plus b sub I, and we're going to be plugging in x sub I plus 1 And then we want to plug in that same point into the ith, or I plus 1th quadratic spline. So that looks like a sub I plus 1 plus b sub I plus 1 times x sub I plus 1 minus x sub I plus 1 plus c sub I plus 1. And then we'll have the same difference in here, x sub I plus 1 minus x sub I plus 1 squared. And you can see we get a little bit of cancellation there on the right-hand side. This is going to be 0, this is 0. And so what we're left with is really just this right here. So we're going to make a couple changes, though, as we go. So we already noted that the a sub i's are f sub I. Let's go ahead and write that. So I'm going to replace a sub I with f sub I. And we have plus b sub I. And we're going to let h sub I just be the difference between the consecutive x values. And it's just going to shorten up our formula here shorten up the formula a little bit, so it looks a little less messy. And then plus c sub I times h sub I squared. And instead of a sub I plus 1, I'm going to write f sub I plus 1. And we're almost to a really helpful formula. I'm going to rewrite this just a little bit more. I'm going to rewrite this as b sub I h sub I plus c sub I h sub I squared is equal to f sub I plus 1 minus f sub I. And let's think about what i's we'd be plugging into this. Okay, and it still makes sense of it. So remember, we do have, we actually have n of these f's, but we only have n minus 1 of the b's and the c's here. So the smallest we could start off for I would be 1, and the biggest we could go and still make sense of this would be n minus 1. Okay, so this is going to take up n minus 1 equations, or this will make n minus 1 equations for us. We're going to get some more by thinking about our first derivative. So we saw with linear splines that it can leave, kind of jagged edges. And so what we can do is if we ensure that the first derivative is equal between the two quadratic splines at the interior nodes, then we're not going to switch derivative at those nodes. It's going to be smooth. Okay? The derivative is going to be continuous. It's not going to have that abrupt change. So let's think about what that looks like. And actually, even before we think about what that looks like, maybe we should find the derivative itself here. So we're going to want to find s sub I, its derivative. Let's go ahead and see what that looks like. S sub I of x is up here. We differentiate with respect to x, we're going to lose that a sub I. Moving on to the next term, we're just going to have a b sub I. And then the last term, this 2 would come down, so you'd have 2c sub I, and then you'd have times x minus x sub I. Go ahead and write that derivative down here. Okay, so we had a b sub I plus 2c sub I times x minus x sub I. And if we want to ensure that the first derivative is equal at the interior nodes, that would look like this. This would look like the first derivative of the ith quadratic spline at the point x sub I plus 1 is equal to the first derivative of the I plus 1th spline at x sub I plus 1. We're going to combine these two pieces of information here, and let's see what that looks like. Well, that's going to look like b sub I plus 2c sub I. We're replacing x with x sub I plus 1. And then the first derivative of the ith plus 1, or I plus 1th spline should look like b sub I plus 1 plus 2c I plus 1 times x sub I plus 1, because that's what we're plugging in for x, and then minus x sub I plus 1. And we can simplify this a little bit. We get b sub I plus 2c sub I, and then this is h, so h sub I is equal to b sub I plus 1. And I'm going to even rewrite that a little bit. To make it a little bit easier to work with here in the future, I'm going to say b sub I minus b sub I plus 1 plus 2c sub I h sub I is equal to 0. And we're going to use this. Let's think about what values of I make sense here. The smallest that we could plug in make sense would be 1. And the largest, because this is a b sub I plus 1, I'm going to write it a little bit neater. The biggest thing you could plug in there would be actually n minus 2. Reason being, if I replace I with n minus 2, then that is b sub n minus 1. And again, we only have n minus 1 splines, so that would be the last b. All right, we have two equations. We're going to consider one more thing. So the last assumption that we're going to make is that the second derivative is 0 at a certain point. So I'm going to fix this here. It is 0 at the first point. And the reason we have to do this is we had 2 times n minus 1 unknowns, but so far we've taken care of n minus 1 here and n minus 2 here, so we haven't quite gotten to 2 times n minus 1. So we need to make one more assumption here in order to make this work. And so it may not be the best option here, but we're going to assume that the second derivative is 0 at the first point here. So let's see what that second derivative would look like. Let me just switch the color here. We have our second derivative of the ith spline is equal to, and I'm going to move up so we can see what the first derivative looked like. Okay, so we differentiate this thing right here with respect to x. All we're going to be left with is a 2c sub I. And so we're only assuming that the second derivative is 0 at the first point. So this implies that C1 is 0. So is what this has done for us is it has reduced the number of unknowns. Now we have, let me point out how many unknowns we have now. We had 2 times n minus 1. And then, again, this was number of unknowns. We've reduced this by 1 now. And let's think about how many equations then that we have. Well, we had n minus 1 equations from the first part. Then we got n minus 2 above. Okay. And let's maybe combine this, or maybe, yeah, combine like terms here. So this would be 2n, and then we have a -1 and a -2, so that's -3. And I think if you were to distribute here, you'd get 2n minus 2 minus 1, which is the same thing. These are both the same number here. They're the same number of equations as we have unknowns now. So we're going to be able to solve this system for all the a sub i's, b sub i's, and c sub i's. And what we'll do is we'll see how we can do all this tomorrow in MATLAB.